Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, it's Mr. T, and today we're going to be talking about functions and inverse functions. So let's get started. So if you remember, we're talking about function notation, which we've been using in class. This is an example of function notation at the bottom. The English version of a function notation is it's asking you to evaluate a function that's defined given some rule, and we're asked to evaluate that function for some given input. Now, functions are like machines. They have an input. They massage the input via some process, in this case these rules, and they produce an output. And for something to be a function, each input must give a unique output. Now, mathematicians like to write things in the most condensed possible way. So this English statement up here, the equivalent in mathematics would be to write it as this. And again, to evaluate this, we're going to do this on the next slide. We would be taking this as our input. -2 would be the input. We would be putting it in for these x's and multiplying. This does not mean the variable f times x. This is the name of the function, function f, and its input. So it's read as f of x. So here I've got two functions up here, g of x with its rule, and h of x, and we've got some examples of evaluating the function. So we would first we want to plug into function g, and we're going to have our input be -3, so this would be 3 minus -3 squared. Now remember, we need to be careful when we evaluate negative numbers squared. If you're using a calculator, make sure you put that in parentheses, so that we get here 3 minus 9 using our order of operations, and -6. So this is our value of g of -3. Okay, so now we're going to use function h and put a 0 in for x. So 3 times 0 is 0, and we get -1. Again, that's the value of this quantity. Now we can use function notation frequently in algebra to create new functions by plugging in letters. So here we could plug in a for x. Now there's no simplification we can do here. If we do for here h, function h, now we're going to replace this whole expression for this x. And we would then want to simplify that, so we could distribute the 3 and combine our like terms. And we could also plug in an expression that uses the same letter x, but this x is different than this x. But we would do the same as we just did up here. Now we're going to put that into our g function. And then if we wanted that in standard form, we would have to FOIL that. If we FOIL that, we get x squared plus 6x plus 9. And then we would distribute our minus. And now we can combine these like terms and put it in standard form. And we have our new function. So again, that's just the basics of function notation. I hope that's familiar to you already. Now we're going to go to the next level, which is called composite functions. So this is where we're going to create a new function using two existing functions. And the notation can be written in one of two ways, g of f of x. So you can see here f of x is the input to g of x. And sometimes we use this notation for our composite functions. This shows up on some of the worksheets I'll be giving you and other places, so I wanted to show both notations. I usually use this notation. I like it better. It's easier to see that this is the input to g, but this notation means the same. If we look at it as a picture, we start and we work these from the inside out. So first x is being input into function f, and it produces an output f of x. That output becomes the input to the g function, and we compute that by taking this input into the g function, and we get our output. So if we look at some examples, so again, we would first evaluate h of 2. So maybe over here we can say h of 2 is going to be 3 times 2 minus 1 is 6 minus 1 equals 5. So now that becomes the input to our g function. So that's 3 minus 25, or negative 22. So the value here would be negative 22. Now we're doing the same thing, except now the order of the functions is different. So let's first evaluate g of 2. Again, we're starting with the inside, sort of like a stack of mixing cups, and we're pulling them out from the inside until we find the one we're looking for. So we get negative 1 for g of 2. So now that becomes the input into our h function. So you can see the order of the composition, the order of which one we do first and second, changes the value. So kind of these order of these functions is not commutative. Now when we use symbols, what we are going to create is the new composite function. So h of x, we don't have to evaluate anything, is that expression. So now we're going to evaluate g of 3x minus 1. And now we put 3x minus 1 in for the x in the g function. And now we can FOIL that. And we would get 9x squared minus 6x plus 1. And we would distribute our minus and combine our like terms to get our final answer. So that function is this composite. Now if we composite the other way, we're probably going to get something different. As we showed up here, they're not commutative. So g of x is 3 minus x squared. So we want to use that as our input into the h function. Distribute our 3 and combine our like terms. And that would be our final answer for this composite. Now the reason we're talking about composite functions is they are related to something we're going to talk about last here, is inverse functions. So inverse functions are ones that undo another function. So the inverse of a function undoes the original function. So these are called inverses. The notation we use is this is the inverse of function f of x. So we're using this sort of exponent of minus 1. But this is not an exponent. It's just used to indicate that this function is the inverse of this function. And I didn't really want to put that dot there. That's not a multiply. If we look at it as a composite function, if we put x into f, we get f of x. If we take that output and put it into the inverse function, since the inverse function is going to undo what we did, we would get back to x. So again, inverse functions undo the original function. Now that fact that they undo each other, and the fact that this is a picture of a composite function, we can get this test for inverse functions. So these two functions, g and h, will be inverses of each other, and this symbol, this stands for if and only if, so both things have to be true. This composite is true, so g of h of x gives you x, and the reverse composite, h of g of x, also give you x. So essentially our input to h is x, we get a function, we put that into the inverse, and we undo it. So we can use that to test here. So we have to evaluate two composites. So I have to evaluate f of g of x here, and g of x was this. So we're evaluating f of 3x, I guess I need to put a bracket here, to the 1/2. So I've got 1/3, and now for the x I'm putting in 3x to the 1/2, and I put that in for this x, so I'm squaring that. Our exponent properties, we multiply those exponents. So I've got 1/3 times 3x to the first when I multiply those. And now there's no exponent here, or it's a 1, I can distribute the 1/3. So 1/3 times 3 gives me 1, or 1x. So that part's good. Now we have to check the reverse composite, so we have to do g of f of x. Now f of x was 1/3 x squared, so we want to take g of 1/3 x squared. So we put that now into this function for the x. So I've got here 3 times 1/3 x squared, and that's raised to the 1/2. I guess I didn't need those brackets. So here we can multiply, so we've got x squared to the 1/2, and we multiply our exponents, so we get x to the first. So both composites gave us x, so we would say that these two functions are inverses, meaning g of x is the inverse of f of x, and also here, I've run out of room, but if I write it over here, f of x is the inverse of g of x. So let's try our second example here and run our test to see if they're inverses. So again, we've got to evaluate, we've got to ask ourselves two questions. Does f of g of x equal x? And does g of f of x equal x? So that's our test. So let's do this path. So I've got f of g of x, which is 1/2 x plus 1. And if we plug that into here, we've got 2 times 1/2 x plus 1 minus 1. So we distribute here, so we get x plus 2 minus 1, and that equals x plus 1. That's not x, so we've just proven that f, in the second example, f and g are not inverse functions, because both of these have to be true. And since this one's false, we don't even need to check that one. So if you're given two functions and asked to be, if they're inverses, again, what you want to evaluate are the composites here and see, do you get x? If it's a multiple choice question, sometimes we can make that process simpler. Now we could still evaluate the composite of each of these functions and see whether you get x. But if we think about undoing, so undoing addition is going to be subtraction. Undoing an exponent of fifth would be the fifth root. So in the inverse of this function, we're going to expect to see a fifth root of something. So we can cross this example out, and we can cross this example out. Now, we have to undo this adding 2, so subtract 2, and we have to undo this adding 3 and subtracting 3. I don't have both of those subtractions here, so we could be pretty safe to believe that this one's not also the answer. So this is going to be our answer. Now if we wanted to verify that, we could evaluate f of f inverse. So that would be f of fifth root of x minus 3 minus 2. Plug this into our f of x, so we're going to get the fifth root x minus 3 minus 2 that went in for this x. Now we've got plus 2 raised to the 5th power plus 3. Here, those 2's cancel out, so we've got the 5th root of x minus 3 raised to the 5th power. When you raise a root to its power, it undoes the radical symbol, so we have x minus 3 plus 3, and we get x. Now, to be complete about this, we should also evaluate the other composite. I'm not going to do that. It is going to check out. Our last step will be, if we're given a function, we want to be able to find its inverse, not have to be given the inverse and test. So to look at that, I've taken a function here, this linear function, which is graphed in red here. And I found its inverse, so this is the inverse of that function. We could run our function test to show that. I've graphed that in blue. And I've graphed the line y equals x. So one of the things that's true for all inverse functions, if you graph the original function and the inverse, they are always symmetrical around this oblique line y equals x. Symmetrical again means they are mirror images of each other. So I've selected on each function some points where the coordinates were nice, where they crossed at the intersections, and I've plotted their reflections. So the reflection of this point is here, the reflection of this point here, the reflection here. And I've written their coordinates, and you could notice that the x and the y here were 0 and 3. Here we have 3 and 0. They're flipped. Here the x and the y is 4, 6, 6, 4. They're flipped. So for all inverse functions, if we graph them, the reflected points, the values of the coordinates are swapped. The x's and y's are swapped. So we're going to use that to create a procedure for how we can find the inverse of a function. So we're going to rewrite our function notation as y equals, and we're going to swap x's and y's, meaning everywhere in the equation there's an x, we're going to replace it with a y, and every place there's a y, we're going to replace it with for an x, and then we're going to solve that for y. That function we get will be the inverse of the original function. So let's go through this example here. I've got a typo here. That's supposed to be example, sorry. So if we first rewrite this in y notation, so this is going to be y, and I'm going to rewrite this to look like this, just easier to do the math. So 5x over 6 is the same as that. Now I'm going to change colors because we're going to now swap the x's and y's. And you don't have to change colors, but it's this x and this x are not the same. So we're creating a new function. So y's become x's and x's become y's. So now I've got to solve that for y. So I'm going to subtract 9. And I'm going to put things on the other side. I'm going to flip the order of the equation. So I've got 5, 6y by itself here because those canceled. And over here we've got x minus 9. Now to undo this, we can either divide by that, or we also know that we can multiply by the reciprocal. So I'm going to multiply both sides of the equation by the reciprocal here. On this side, everything cancels out, so we have y equals, and I'm just going to move that constant to the front. Now that function is the inverse of our original function. We could, if we want, distribute, so let me just go ahead and distribute the 6/5. And then we can put it back in function notation. So by the process we did, this function now is f inverse. It's the inverse of our original function. If you wanted to verify that we had properly done the math, we could evaluate f of f inverse and show that we get x. I'm not going to go through that. This video is getting long, but you can see here the procedure. So good luck in working with functions, composite functions, and inverse, and I'll see you around.
Are you ready? Are you ready? Oh, are you ready? ready? Are you ready? Are you ready?